A very conceptual illustration of two DNA robots collectively performing a cargo sorting task on a DNA origami surface. Image Demon Lewin. The classic 1966 American science fiction film Fantastic Voyage, a submarine crew was miniaturized and injected into a body to fix a blood clot in the brain. That's obviously not how future medical science is going to work, but the notion of creating microscopic machines to perform complex tasks is certainly on point. A recent advance, in which robots made from DNA were programmed to sort and deliver molecules to a specified location, now represents an important step in this futuristic direction. It's still early days for nanotech, but new research from the California Institute of Technology is showcasing the tremendous potential of this pint-sized technology. A Caltech research team headed by Anupama Thubagare and Lulu Jian has built robots from DNA, and programmed them to bring individual molecules to a designated location. Eventually, this technology could be used to transport molecules of many types throughout the body, which could potentially transform everything from drug delivery to how the body fights infections to how microscopic measurements are made. There are currently three emerging fields within DNA nanoscience: the science of creating molecular-sized devices out of DNA, the self-assembly of nanostructures from DNA strands, molecular computation and data storage, and DNA robotics, which is the focus of the study published today in Science. The central premise of DNA nanoscience is that, rather than creating molecular devices or systems from scratch, we can leverage the power of nature, which has already figured much of this out. If and when we finally master molecular machinery, we'll be able to build microscopic-sized robots with programmable functions and send them to places that are otherwise impossible to reach, such as a cell or a hard-to-reach cancerous tumor. Futurists have long speculated that nanotechnology, the engineering of materials and devices read more. In prior experiments, DNA robots demonstrated their ability to perform simple tasks, but this latest effort ramped up the level of complexity considerably, while also opening a path towards the development of general-purpose DNA robots. It is the first time that DNA robots were programmed to perform a cargo sorting task, but more important than the task itself, we showed how this seemingly complex task, and potentially many other tasks, that DNA robots can be programmed to do uses very simple and modular building blocks, explained Qian in an email to Gizmodo. This is also the first example showing multiple DNA robots collectively performing the same task. For the new study, the researchers designed a group of DNA robots that could collectively perform a predetermined task that had them walk along a test platform, locate a molecular cargo, and deliver it to a specific location. The bots were able to do this autonomously. Conceptual illustration of the molecular cargo delivery system. Image Elamaru Studio. Each robot, built from a single-stranded DNA molecule of just 53 nucleotides, was equipped with legs for walking and arms for picking up objects. The bots measure 20 nanometers tall, and their walking strides measured 6 nanometers long, where 1 nanometer is a billionth of a meter. For perspective, a human hair measures about 50,000 to 100,000 nanometers in diameter, so the scale we're talking about here is ridiculously small. For the cargo, the researchers used two types of molecules, each a distinct single-stranded piece of DNA. In tests, the researchers placed the cargo onto a random location along the surface of a two-dimensional origami self-folding DNA test platform. The walking DNA robots moved in parallel along this surface, hunting for their cargo. To see if a robot successfully picked up and dropped off the right cargo at the right location, the researchers used two fluorescent dyes to distinguish the molecules. Scientists are not at the stage yet where they can program robots of this size to have built-in memory, so instead, the robots were designed to match their cargo. We designed specific drop-off locations for each type of cargo. If the type matches, the drop-off location will signal the robot to release the cargo, otherwise the robot will continue to walk around and search for another drop-off location, explained Qian. You might think that the robot is not smart. But here is a key principle for building molecular machines: make individual molecules as simple as possible so they could function reliably in a complex biochemical environment, but take advantage of what a collection of molecules can do, where the smarts are distributed into different molecules. The researchers estimate that each DNA robot took around 300 steps to complete its task, or roughly 10 times more than in previous efforts. We successfully programmed complex behavior in DNA robots and compartmentalized each task using DNA origami, said Thubagare. In experiments, 80% of cargo molecules were sorted, so there's room for improvement. Qian and Thubagare hypothesized that not all molecules were correctly synthesized, or that some parts of the robot or testing platform were defective. Much more work needs to be done to figure this all out, and to test the DNA robots under different environmental conditions if we're ever going to have these things working in our bodies. This new study offers a viable methodology for scientists to continue pursuing. The biggest implication that I hope the work will have is to inspire more researchers to develop modular, collective, and adaptive DNA robots for a diverse range of tasks, to truly understand the engineering principles for building artificial molecular machines, and make them as easily programmable as macroscopic robots, said Qian. Science.